So here we're going to introduce you to the amines, and we'll just go through a basic synthesis of these amines. And part B, I'll try to expand upon the reactions of amines, and also we will try to look at some biochemical features of these amines. And we'll look at also some heterocyclic species that have these nitrogens present in them. So yeah, let's briefly just go through this quite quickly. You can see that these amines are organic derivatives of ammonia, and just like water, yeah, which has alcohol derivatives, here you have ammonium derivatives. The nitrogen atom itself, yeah, has a lone pair of electrons, so we realize Lewis basicity and of course quite good nucleophilic abilities, much stronger than oxygen because it is nitrogen, which is less electronegative than oxygen, i.e. the electrons are less held. You can classify these as primary, secondary. You can see here, for example, the primary, it's just got one R group. Yeah. Oh, got you there, didn't I? Yeah. Secondary, because there's two R groups. Yeah. Tertiary, because there's three R groups. Yeah. And here we have an interesting thing. We have these guys we can isolate. They're quite stable. Yeah. We have quaternary ammonium species. There's four R groups, and the nitrogen itself has a positive charge. Quaternary ammonium salts. There's nomenclature. Something like this you can either just call it methylamine or cyclohexylamine, or you can give it a more interesting name like methylamine. But in this case here, you can see that we have typical organic compound, right, where we talk about the longest chain. So here you can see that we have this propane unit, and on carbon 2, yeah, we have the nitrogen, and so that's a 2-propanamine or a propan-2-amine. But we also got to tell the reader, yeah, how many other groups are present on the nitrogen and what type of groups they are. In this case, we have a methyl present, and so we tell the reader that we have a nitrogen methyl or an N-methyl. So now it's N-methyl propan-2-amine. Yeah, it's not too bad. So for example here, yeah, typical of nitrogen, we can easily alkylate it. So you can see the bimolecular attack here, yeah? And you'd release that bromine, of course, and so you would end up with a nitrogen flanked by the ethyl that you just added and the methyl that was present initially, those two hydrogens still present. So here you have a quaternary nitrogen. You can add a bit of base and stuff like that in step 2 to remove that hydrogen bromide. Remember that the bromide itself is the counter ion to the ammonium salts, and that would then give you this species here, which is the methyl, yeah, ethylamine or ethyl methylamine. Yeah. We gotta mention quickly that yes, a naked amine like this, primary amine like this, you can see that it's on its own. So of course it adopts sp3 hybridization. Got 1 block, 2 block, 3 blocks, 4 sp3. However, here, don't be misled, it is conjugated to a carbonyl, i.e. it's more stable for that lone pair to adopt, yeah, a strategy of having a p orbital perpendicular to the plane of a molecule, yes, where the nitrogen is sp2 hybridized. So you can see that these guys also will be sp, well, I would have p orbitals perpendicular to the plane of the molecule. Physical properties of amines, it's kind of obvious that primary and secondary amines have NH bonds, and so therefore they would be species with hydrogen bonding. The hydrogen bonding is much weaker than that in alcohols, as you can see from the boiling points. The same thing will be reflected in the melting points. Why? Because the NH bond is less polar than OH. Quaternary, tertiary amines, cannot hydrogen bond because there is no NH present, of course. Yeah? As far as solubility is concerned, they got decent solubility in water, but of course, again, they'll be less soluble in alcohols. However, you should realize, like alcohols, yeah, the greater the molecular weight, i.e. the carbon chain, then the less soluble they are in water. Yeah. You can see here, we can easily make a lot of these guys soluble, and how we do that is, and a lot of drug companies would do this as well, is they literally would treat it with a bit of acid, and you get the ammonium salt, and the ammonium salt, now you can see, is ionic, and so that will be soluble in water. You do not see this event with amides. So what I want you to do is go ahead and try to read some more about the physical properties of these amines. The other, of course, is not as bad as the thiols, but it's still pretty awful. Exactly. You can see why we study amines, because like the carbonyls, these guys are ubiquitous in biochemistries. So you think about proteins, nucleic acids, most pharmaceuticals, contain some sort of functional groups. So you can see, for example, the dopamine, sorry about that. We have the dopamine, and the dopamine, sort of reminds you, of all them other things, right? Because they should remind you of dopamine, because you can see here, we got this diethylamine thing going on. You see that next to an aromatics? Can you see that? So all of these guys say, for example, nicotine, which is rather addictive, is an amine. Quinine, which is very useful. Strychnine, very useful. All of these species are quite useful, during certain circumstances, but of course some of it are open to abuse. So what amines, they're included in neurotransmitters, bioregulators, vitamins, alkaloids, amino acids, you name it, there are amines present. We talk about neurotransmitters, we know that these guys are the species that are released at the end of the nerves, and that travels through the synaptic gap. So we get this species binding to a chemical receptor, and that will trigger your nerve impulse, neurotransmitters. Number of physiological active compounds are derived from the phenylethylamine, like we can see here adrenaline, mescaline, and of course you can see exactly what's going on with acetylcholine, some sort of ethylamine. So note that ethylamine, right, next door to some sort of conjugation. Basicity of amines. It's terribly important that you realize by now that the amines have a certain Lewis basicity. You can see the Lewis basicity, or you could even think of it as a Bronsted basicity in the sense that it's a Lewis base because it's donating electrons. It's a Bronsted base because it's accepting protons, yes? So what we have reactants and products. And so we have Kb. In this case, this is water, which is a constant. So we have Kb is, of course, the conjugate acid, times the concentration of hydroxide over the original amine value. And you can see Kb, yes, they're very, very small, i.e. it's quite basic. Preferably, I like to use the Ka as a comparison between different bases. Now, think about this for a second. You have here a acid base reaction. So we're donating protons at the present moment from left to right. If your base is weak, then this is a really powerful, acid. Why? Because weak base means stable conjugate base compared to strong acid. However, you should realize by now, that we're looking at the basicity of the species. Right? So the stronger the base, the weaker the acid, i.e. the higher the pKa. Right? Because the stronger the base, then the more this reaction will stay to the left, in its conjugate acid form, and therefore there will be a copious amount of the conjugate acid and very little protons, and so this will be very small. If the Ka is tiny, then the pKa, which is minus log Ka, will be large. So small Ka, very large pKa. The weaker the conjugate base, the weaker the conjugate acid, the stronger the base. Look at this problem and try to tackle this, and we'll look it over in class tomorrow. So I'll put this on pause. The pKa of the conjugate acids of amines are pretty standard. Doesn't matter if I got primary, secondary, or tertiary amines. You can see that they're relatively weak acids, i.e. you can see 10.7, 10.5, 11, all about the same value. So I don't really care about this lot. What I care about, and what I think is more important, is when you compare the amine chemistry of nitrogens that are associated with rings. So here, for example, I have aniline, and aniline is much weaker than pyrrole, because we're looking at the pKa values, right? Where you say the aniline's conjugate acid is much weaker than pyrrole. Why? Because remind yourself that pyrrole, the conjugate acid of pyrrole is meaning that dissociation of that proton will regain your aromaticity. So we have in pyrrole a very stable conjugate base. Hence, the conjugate acid of pyrrole is quite good. So strong acid, yeah, a stronger acid than that of aniline, i.e. the ammonium species of aniline. Why? Because this is still an accessible lone pair. This lone pair is in the aromaticity. It's not accessible. Here with pyridine, this is also accessible, and more so than this lone pair, because remind yourself that this lone pair is in resonance with the ring. This lone pair sits in a naked sp2 hybrid, yeah? Or is naked in an sp2 hybrid orbital. Okay, so this is your strongest base. Remind yourself of this slide we covered some time ago when we were looking at aromatics. And we were looking at this and we looked at the 3 different nitrogens that are present. And we asked you to devise a strategy to find out which species is the most basic and which species is the least basic. And of course, in histamine, you have a nitrogen here, which is in an sp3 hybrid. It's a primary amine in an sp3 hybrid. And here we have a pyridine nitrogen. It's a pyridine nitrogen. And here we have a pyrrole nitrogen. Yeah? If we look at that N1 is a pyrrole, N2 is a pyridine. Let's call this N3. Yeah? If we look carefully, you can see it's quite stark, right? This is in the pyridine nitrogen sp2 hybrid orbital. Yes? And is quite accessible. Yes, so of course it's good base, good nucleophile. Here on the other hand, yeah, this lone pair is in the aromatic ring and it's inaccessible. So it's a poor basic nitrogen. Or this nitrogen shows poor basicity. This fella is in an sp3 hybrid. It's a naked amine. So it's very powerful base, yes? We can also look at the substituent effects on basicity of aniline. Remind ourselves that aniline has a pKa of 4.6. Yeah, and the reason why the pKa is not as great as pyridine is because this lone pair is resonating in the ring. It stands to reason if we have an electron donator, i.e. an activator, here we have an activator donating electrons via resonance, then of course it will make that lone pair more available. On the other hand, here we have a deactivator, and so that lone pair, yeah, it's pulling back on that lone pair, and so that lone pair, yeah, being pulled back into the ring by the nitro, and so it is a much weaker base. And it's reflected here in this energy diagram because you can see here, yeah, that the reaction, yeah, that is due to protonation is much less, i.e. this will release its proton, yeah, at a much less rate than the nitro species. So at a much greater rate than the nitro species. So this one is greater because the activation energy is lower. Yes? Think of the activation energy here is much for this one than for that fella. Yeah. So it's all the way down here actually. Yeah. So you can see that this one is reluctant to give up. Yeah. You can see here, for example, yeah, that there is these guys here are less acidic, i.e. greater bases, and then these guys here are more acidic, i.e. less basic. Remind ourselves how we derived the Henderson-Hasselbalch equation. Yeah, we looked at the equilibria between the acid and the base. And in this case here, pH, in the Henderson-Hasselbalch, pH equals the pKa plus the log of the conjugate base over the acid. And when we look at this transmitter, this neurotransmitter dopamine, which has a pKa of 10.6, here we can add 10.6, and the pH, of course, in this buffer is 7.3. In a living cell, it's buffered at 7.3. You can imagine a buffer being with some hydrogen phosphates or some carbonates, but usually some phosphates. But you can see here, all we got to do is manipulate this lot, yeah, and then we'll end up with minus 3.3. Yeah, so you take this guy, put it over the other side over here. You got minus 3.3 equals the log of that. So you just anti-log 3.3, and of course you get 5.5 times 10 to the minus 4. Yeah, if you inverse that, then you would realize by now that the ratio of the conjugate acid over the conjugate base is 2,000 times that of the neutral amine. You see? So amines are less than 99.9% protonated at physiological pH. Right? So it's greater than 99.9% protonated at physiological pH, like that. Separation. We went through this before. If you have a mixture of base with other, say, neutral organics, then all you got to do is acidify, and there you'd have your ammonium salt. Your ammonium salt will then pass into the aqueous phase. Yes. And then once you have that aqueous phase, then you can basify that aqueous phase to release your pure amine. Amine preparation. Here we're going to be looking at reduction. Yeah, so just about any nitrogen compound that you have, you can come across, just you can reduce it, yeah, with some sort of reducing agent, and dihydrogen somewhere deoxygenate. And then we'll talk specifically for few reactions, including the Gabriel synthesis, which is a very beautiful way of making primary amines. Every single one of these fellas here, right? Amines, nitroamines, azides, nitroamides, all of them we can reduce to amines. So let's have a look. A lot of them we've come across before. Say, for example, here, yeah, we briefly mentioned it before, where if we have a nitrile, we're looking at carboxylic acid derivatives, we can generate nitriles. If we have a cyanide, the cyanide can have a nucleophilic attack in this case a bimolecular attack, on that primary carbon, we realize the nitrile, remember this is a coupling because you just form the carbon-carbon bonds, and then we just go ahead and with our good old reliable lithium aluminum hydride, yeah, we go ahead, reduce it and quench out with water. That will give us a primary amine. Here you can see if we got azo species, so this azide, again we can do a bimolecular attack. We end up with the azide, and then we have lithium aluminum hydride. We release dinitrogen, and of course we again have a primary amine. This is quite pretty because what do we have here? We have here the reaction of an amine with the acyl chloride. Yeah, depending on what type of amine you're using, then of course you can see that reduction with lithium aluminum hydride, a deoxygenation, I should say, yeah, which we've come across when we looked at carboxylic acid derivatives. Yeah, and in this case here you can see we had a tertiary amine being formed. You could even start here, for example, with a secondary amine, yeah, attack this fella, and now one of these fellows would be a hydrogen. Should I say secondary or primary amine, sorry. So one of these guys would be a hydrogen, so you would end up with a secondary amine. Yeah? If you used ammonia, then this would be, yeah, NH, and so once you reduce it, then you would end up with a primary amine. It says here, what would you expect if you combine ammonia with an aldehyde and then follow up by a reduction? Have a think about that, and then we'll look at it in class. So I want you to think about it, and I pause, and this is exactly what I need. So pause, you work on that, and we talk about it in class. You can see a wealth of reactions here with ammonia and other amines. So for example, here with ammonia, yeah, we end up with this imine, typical. And then once we reduce that imine, then you can see we end up with a primary amine. Here with the primary amine with the ketone, we end up with another amine, and of course reduction realizes a secondary amine. And of course you can see your secondary amine would give you a enamine, which you can then reduce up to give you the tertiary amine. All of these reactions can be really generalized, yeah, like this, where you have that sort of thing. So in this case here, we're looking at a primary amine with a ketone, and you end up with a secondary amine once you have reduction of the imine. You can see that the iminiums, instead of using this harsh lithium aluminum hydride, we can use these cyanoborohydride. It's much cleaner and much safer than the lithium aluminum hydride. And because the imines are much more reactive, then this is quite good to use. Yeah? So you can see that in both cases. Here we have imine type systems, and the reduction is very clean. Requires no quenching. So we can easily answer something like this, because you can see, for example, that this is the cyanide, and of course we're going to couple. So really think about it, right? We couple and then we reduce. So really we got a nitrile. It's a 1, 2, 3, 4. So then it's going to be a propan, and the nitrogen, of course, is terminal, and so that will be the propanamine. Huh? Is it propanamine? No. Propan is free, right? So it's going to be butanamine. Yes. All right. Excuse me, because course it is 4. Here we have an azo group, and of course the azo also, the azides would also have attack on this electrophilic center, and of course, so this is your leaving group, typical biomolecular, and then we reduce. The reduction, releases dinitrogen, leaving you with an amine. We only have 3 carbons, so of course you can see that our product therefore will be the 1-propanamine. Work on those for us, will you? And then here, right, this is a sort of a cumulative of what we've done in the past, and and stuff that we're looking at now. And it says here, identify the type of compound X present in the following, and you've isonitriles, nitriles, nitrite, and oximes. So what I want you to do is have these guys flank them into R groups or something and figure out which one is X. So there's a reduction to form an amine, and there's a hydrolysis under acidic conditions to form an acid. So which one is it? I will pause here. I'll advise you to pause here as well, and we'll look over that in class. I kid you not, when you look at these other synthesis for amines, it's sort of like a who's of the stuff that we reviewed in the past, because here, for example, you can see we take this amine and react it with a carboxylic acid. This carboxylic acid most likely was generated from the Hell-Volod-Zelinsky reaction. If you remember rightly, in the Hell-Volod-Zelinsky reaction, we brominated the carboxylic acid with phosphorus tribromide in the presence of bromine. So that alpha carbon of the carboxylic acid, that's the only way we can do that bromination. And now you can see the nucleophilic attack on that carbon, and that realizes your amino acid. In the case of nitroarenes, for example, why we've done this when we did aromatic chemistry, we use this species here, the nitrous with sulfuric acid. Remind yourself that the sulfuric acid dehydrated this to give you the nitrous, and then you can reduce zinc HCl, iron HCl, H2 palladium with palladium black. These are good reducing species, and they will give you the aniline. And this one's kind of obvious. This is from stuff you did back in ether chemistry in Organic 1. And you and I know, because it's a base, because this is a base, then of course the attack will be at the least substituted carbon. So biomolecular attack at the least substituted carbon, and then of course, you can then get the alkoxide intermediate. Once this strained ring is open, you can then quench that alkoxide, and therefore you end up with this beautiful hydroxyamine. So here's a question that that we should review. You can see we have N-ethyl pyrrolidine. So what we got to do is remind ourselves to what pyrrolidine is. Pyrrolidine is this species, of course. We saw it in the storquinamine. So N-ethyl pyrrolidine, is really pyrrolidine with an ethyl attached to it. Yes? So how would you make something like this? It says by an acylation. So let's see what this is all about. Acylation, meaning that you had from there, you had to have an acyl group involved to get from here to there. Yeah? So it's a 2-carbon, addition. Let's see exactly what is going on. I'll just go through it real quickly and then we'll explain it. You can see, that we require the ethyl group to make this a tertiary amine, and it's an acylation, so we need an acid chloride. In this case, the 2-carbon acid chloride is acetyl chloride. Yeah, and then we're going to reduce it, to give us the pyridine. So the mechanism would look like this, or the reaction would look like this: pyridine plus the acetyl chloride. Yes, you have the addition elimination, so i.e. the substitution of the chloride with the pyridine, and this is your product. And then when you reduce and quench, then this is the final species, pyridine with the ethyl unit attached to it. Why don't you do these at home? I think it's in the slides that's uploaded on web courses. So make sure you do those. I'll pause and then we can tackle those when we meet on the next time we meet. Here we're looking at quite an interesting drug, especially right now when we're thinking about the COVID and the antivirals that we need to treat it. Yeah, this one can be used as sort of like a mild treatment of influenza, Tamiflu. And it's quite simple. You can see here we have this aziridine ring, which is quite strained. And so we use our N3 minus, and attack the least steric portion of the ring. And of course you can see that this is the least steric portion, because this one, you can see these guys, this is a lot more steric, it's a lot more than this one, you see. So this is the least steric side compared to that one, you see. Alright, and so compared to this one, so this one is more this one is less steric, you see. Alright, so the attack will occur here. You can easily quench out, and there you have the substitution. There you have the azide. The amine can now be acylated. We've seen this before. And after acylation, there's mild reduction. And voila, you have your drug. Right? You can spend it, and we save a lot of lives with that. All right. What else can you think of with this? Here, for example, we have these things on 300 gallon scale. So this is monstrous, right? So this is dead cheap to make, All right, we have stuff like this. You can see we've made an amine of some sort. And then there's the reduction. Kid you not? A few steps later, you can see that we've made the cough suppressants, and here we've made the zeta-cetron, and both Eli Lilly and Dompe made a lot of money from these guys, All of these, I think, if I gave you them, you could, as a project, you could literally make it on paper. So, this is an important reaction for us, and you should remind yourself of the mechanism and remind yourself of the reagents. This is the Gabriel synthesis. We have phthalimide, right? And phthalimide, has a quite fairly acidic proton. You may wonder, why is it? Amides are usually Yeah, hard to deprotonate. But this amide is because it's flanked by 2 carbonyl. So we can easily deprotonate here with a hydroxide. Yeah? And we end up with the potassium salt. The potassium salt has this nucleophilic nitrogen, so it's a pretty decent nucleophile, which we can then use for a biomolecular attack on the alkyl halide. And so now we have our nitrogen carbon bond. This is the species that will give you your primary amine. Yeah, so all we got to do really is we got to treat this phthalimide conjugate to either an acid, or we can treat, after treating with the acid, we can treat it with the hydrazine. Either way, we released either the ammonium salt and this final product here, the amine. Of course, remember that this is a base, but not only is it a base, but we literally can get rid of this dicarboxylic acid by treating it with the hydrazine. So this is very nice. Could I ask you, why is it that we only use primary amines? Primary alkyl halides, sorry. We should not say, well, we should say the attack works for primary alkyl halides, not primary amines. We should correct that. And of course, it is SN2. So it's a biomolecular mechanism, so we have to have primary species, yes? And there's nothing else we can do about that. Let's move on. So a question like this is kind of simple because you can see that we have 1 nitrogen involved. We've just been talking about a phthalimide. So of course you can see here, phthalimide base followed by the quenching, right? Personally, why couldn't you use this fella? Because if you use the cyanide, that would be increasing this carbon chain with an extra carbon, yes? Alright, why couldn't you use this fella? Because if you use that azide, if you think about it, if I deploy this reducing agent, I'll reduce this double bonds. Alright? And if I use straight up ammonia, what's that going to give us? It's not very good. That's the most efficient way to get to the amine. So that's the end of the part A. The next time we have a chat in these presentations, we'll be talking about the reactions of amines. So if you notice, acylations we've already been through before, and the nitrosations and dietization of arenes, we've also done when we did aromatics. We've talked about the nitrogen heterocyclics before, but this time around what we're going to look at is we're going to look at electrophilic substitution on these heterocyclics, and also some nucleophilic substitution of halo pyridines. So we look forward to that. See you then.